All right, so we're going to be starting chapter 3, lesson 3, solving systems of inequalities by graphing. So we're going to learn how to solve systems of inequalities by graphing, and we're going to determine the coordinates of the vertices of a region formed by the graph of a systems of inequalities. So some vocabulary to keep in mind is what a systems of inequalities is, right? So we've talked about systems of equations in previous lessons. Now we're going to be moving on to systems of inequalities. So let's take a look at this. So it says graph of a system of inequalities is, to solve a system of inequalities, we need to find the ordered pairs that satisfy all of the inequalities in the systems. One way to solve a system of inequalities is to graph the inequalities on the same coordinate plane. And the solution set is represented by the intersection of the graph. So let's take a look at what that means. Here's an example that says, solve each system of inequalities by graphing. So let's look at the first one. So let's look at A. So the system of inequalities, right? So these two inequalities creates the system. Is y greater than negative 2x plus 4, and y is less than or equal to x minus 2. So let's go ahead and we're going to start by graphing the first one, right? So we make our boundary line with a y-intercept of 4, slope of negative 2. It's a dashed line because it's just a greater than symbol. And then all the solutions that satisfy the inequality are the points above the line, so that's what's shaded. Now let's go ahead and let's graph the second inequality. Y is less than or equal to x minus 2. So that would look like this, where you have a y-intercept of negative 2 and a slope of positive 1. It's a solid line because it's less than n equal to. And then all the shaded region below the line would be where your solutions are. So now that I've graphed each one of these inequalities separately, let's go ahead and look at them on the same coordinate plane. So if I look at them on the same coordinate plane, it looks like this, right? So I'm taking both of them and I'm merging them into one. So when I look at this, I know that the yellow represents the first inequality. I know the purple represents the second inequality. And where they overlap would be my solution set. So if you look, it kind of creates like three regions here, right? Region 1, Region 2, Region 3. Well, Region 2 is where the only area that satisfies both this inequality and this inequality. So if Region 1 and 2 represent the solutions for this inequality, and Region 2 and 3 represent the solutions for this inequality, then it would be safe to say that this green area represents where the two graphs overlap. So the intersection of these two regions, right, Region 2, is where the solution set is for the inequalities. So I would say that the solutions occur here. So the answer to a systems of inequality is a graph, and it is where the two inequalities overlap, where their two areas overlap. So any point in this green region and any point on this line, but not on this one because it's dashed. This one, yes, because it's solid, would be a solution, would be an x and y coordinate that would work for both inequalities. So this is really similar to what we did before, where we had intersecting lines that created a solution for systems of equations. But in systems of inequalities where we had shaded areas, it's where the two shaded areas overlap. Let's take a look at the second one. So here I have my first inequality is y is greater than x plus 1. So that graph would look something like this. The second one is the absolute value of y is less than or equal to 3. So that would be a graph like this, because the inequality of y, the absolute value of y less than or equal to 3 can be written as y is less than or equal to 3 and y is greater than or equal to negative 3, right? When we talked about solving inequalities, it was the distance, right, from both the positive and negative version of that, right? So the positive one is written exactly the same, so with the exact same symbol. The negative version, I have to flip the inequality symbol. So these would be my two inequalities that would show this thing sandwiched together here, right? All y values less than positive 3, all y values greater than or equal to positive. Actually, these should both be solid. And then when I look at them together, these two inequalities, when they're graphed, again, my solution is where the two areas overlap. and my two areas overlap right here, right? So the blue is all this stuff, the red is all this stuff. And so my solution occurs where the two shaded areas overlap, right? So graphing all the inequalities in the same coordinate plane, this shaded region would be the common one to both of them. So this area would be my solution, right? Anything along this point, or any point along this line or this line, and then sandwiched between these two regions here. So it is possible that two regions do not intersect, right? So just like we had a no solution for two lines, you can have a no solution for two inequalities. In such a case, we say the solution is an empty set, and this is a symbol for an empty set, or you could also say no solution exists, because the solution would be the x and y points that satisfies both of them. So let's go ahead and look at the graph of those. So if I graph the first inequality, right, y-intercept of 1, slope of positive 1/2, right, up 1 over 2, up 1 over 2, and again, dashed line because it's not equal to. And then I'm going to go ahead and graph the second one. That one has a y-intercept of -3. Again, a slope of 1/2, up 1 over 2, up 1 over 2. Again, a dashed line, everything shaded below here, everything shaded above there. Now, if I were to look at these two graphs on the same coordinate grid, it would look like this. Now, if the solution is where the two shaded areas overlap, do they ever overlap? The answer is no, they don't. So since the two inequalities never overlap, the solutions have no points in common, so the solution set is an empty set, or there is no solutions. So let's go ahead and look at another example. So here it says write and use a system of inequalities. So here's an example. It says, when NASA chose the first astronauts in 1959, the size was important since space available inside the Mercury capsule was very limited. NASA wanted men who were at least 5 feet 4 inches, but no more than 5 feet 11 inches tall, and who were between 21 and 40 years of age. Write and graph a system of inequalities that represents the range of heights and ages for qualifying astronauts. And unfortunately, back in these times, in 1959, they did not look for women, which is its own social thing that it was meant to be dealt with. But at this point, they were kind of stuck back a little bit further back. But anyways, so as we're expanding on this problem, let's let h represent the height of an astronaut in inches. So it says the acceptable heights were at least, so at minimum, 5 feet 4 inches or 64 inches tall, and no more than 5 feet 11 inches or 71 inches tall. So it had to be something between 64 and 71. We can write this information as two inequalities. We can say that h has to be greater than 64 and h also has to be less than or equal to 71. Let's let a represent the age of the astronaut. Well, the acceptable ages can also be written as two inequalities. We would say that the age, or a, has to be greater than 21, and the age has to be less than 40. So a has to be more than 21, but less than 40. So it says graph all the inequalities, and then any ordered pair in the intersection of these graphs is the solution set. So these, notice how they only have one variable, so they're going to represent vertical and horizontal lines. So this is what the graph would look like. If my height was down here and my age was down here, and it doesn't matter, you could have flip-flopped these, but I know that my height has to be between 64 and 70, which would be all this area here. And then my age has to be between 40 and 20, which is all this stuff here. And so my solutions are anything in this shaded region, right? It could be on this line here, but not on either one of these lines, again, because of the inequality symbols. So this area shows the constraints for age and height of what they were selecting for astronauts in 1959. So what about finding vertices of a polygon region? Sometimes the graph of a system of inequalities forms a polygonal region. You can find the vertices of the region by determining the coordinates of the points at which the boundary lines intersect. So let's go ahead and take a look. So here it says find the coordinates of the vertices for the figure formed by x plus y is greater than or equal to -1, x minus y is less than or equal to 6, and 12y plus x is less than or equal to 32. So here it says graph each inequality. The intersection of the graph forms a triangle. So that would be this. So here is x plus y is greater than or equal to -1. So that'd be that line there, and it would be shaded on this side. X minus y is less than or equal to 6 would be this line shaded in this direction. 12y plus x equals 32 would be this line shaded in this direction. So the overlapping areas would be created by this triangle here. And so our job is to find the coordinates for the vertices. Well, luckily, these two vertices land exactly on whole numbers. So you can easily count like, oh, -4, 3 is that vertice. And then you can count this way, 8, 2 is that point. So that's that vertice. So if you notice, this point does not fall perfectly on the grid, which means this is not perfect set of whole numbers. So how could we find this point? Well, the way that we could find this point is by using these two equations, because we know how to find where two lines intersect, right? That's just a systems of equations problem. So if we take these two equations, right, we can solve them either by using substitution or elimination. And if I look at this equation and this equation, they're set up pretty easily to use elimination. So let's go ahead and take these two equations, and let's go ahead and add the equations together to eliminate y. Because if you notice, I have plus y and minus y. So here's my elimination problem set up using those two equations. I know x plus x would give me 2x. Positive y plus negative y makes 0. And then -1 plus 6 makes positive 5. And so now I can just solve for x. So if I divide both sides by 2, I get x equals 5 over 2. So that's just a fraction. I can leave it like that. You could write it as 2.5, but not necessary. So now we've solved for the x coordinate. So now what's left? Solve for the y coordinate. And we can do that by substituting 5 over 2 in for x into one of the original equations. I'm going to go ahead and use the first one just because it looks a little easier. So again, there's my x. I'm going to substitute 5 over 2. So once I do that, then I'm going to go ahead and subtract 5 over 2 from each side, which gives me y equals -5 over 2, because this is really like -5 over 5. Or sorry, -2 over 2. So that would give me -7 over 2. And then now I have my x coordinate and I have my y coordinate. So now I know that the first two coordinates were -4, 3 and 8, 2. So the third coordinate is just the x and y coordinate that I found, 5 over 2 and -7 over 2. So that third vertice, notice how it's not whole numbers, but easily defined using this elimination method. Thanks for watching. Let me know if you guys have any questions.